Yo, what's going on? I'm going to teach you how to do calculus, or actually not how to do it, but what people have been talking about and what might seem scary or confusing to most people that have only heard about it in like passing or like, with dread. Oh my gosh, I'm taking calculus. Okay. So, terrible humor aside, let's get into it because I've seen like some videos about this, but often they like ramble or they're like so focused on making under 2 minutes that it's like not very, well thought out. But so we got this guy Newton, right? I'm not going to draw because I have terrible drawing skills. But he invented calculus, not because he was bored and he had nothing to do, but he wanted to map out how the world works. So let's have two graphs. Let's have position versus time, right? So like the car, and then let's have its velocity versus time, or speed versus time if you don't know about physics. So and let's say it's regular. Imagine this is a straight line. Straight line. Ignore my kindergarten drawing. Anyway, so let's go. Let's get into it. So this car right here, it's not moving. It's not going anywhere. Zero position. Over here, you can see it slowly picking up speed. Oh, imagine this is exponential, by the way. Imagine this is like a good looking parabola. But so just like see how he's picking up speed and he's also moving. His position's also increasing. But here, his position's increasing a lot more rapidly with regards to time. The bad boy derivative, what you've heard maybe, or maybe you haven't, will take the pitch, the slope, the incline, incline, not inkling, not, I don't want to get sued by Nintendo, the incline at any certain point. So like this point I looked right here, and like I draw a straight line through it, that's going to be its tangent line, its derivative at that point. And you might be saying, whoa, you drew a line there. What's the big deal? Well, slope is the rise over run, right? This is the position over time at a certain point, or the meters per second. What is that? That's velocity. But bang! You just found the velocity at that point. Just imagine like I could actually like circle this in a different color, but the thicknesses are weird, so it's going to be like even more big. See, like I can change the size. Anyway, so you just found the derivative. What that does is it takes the slope at any point in this line. It can be anything. It can be like a woo 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 woo, and it'll take the line. The thing is, derivatives don't work at like crazy points like this, since obviously the slope's changing too much. Like we'll get into that later. That's why there are things called limits. Or actually, I'll transition for a second. Limits are like, for example, you got this thing going, whoop, and it goes whoop. Obviously, this jump isn't possible in ordinary things, that ordinary physics, so in the world and all that stuff. So derivatives don't work, since that's like you're trying to find the change, the instantaneous change, and that doesn't work right. Math will look at that and say like, bro, what you want? Okay, bro, why am I moving this? Okay, so let's get to the velocity now. So we just talked about the derivative, the thing that basically finds the line on the moving line. Big words, doesn't make much sense. Hopefully it makes sense. And so now there's something called the integral, the second part, the dynamic duo, the LeBron James and I think it's Anthony Davis now. Anyway. So the integral, let's just say you stop here at like 6 hours after driving for 6 hours in constant acceleration. This isn't realistic in any way. I don't think anyone would drive for 6 hours constantly accelerating unless they're in like a minivan. Okay, so now we got this thing called the integral, and so integral takes the area under the curve. In this case, that would be the velocity on this side and the distance in the other, because you know how like you multiply the side by the side, normal area things, and that would take this bad chunk right here, and you would find the total position. If I took the integral here, it wouldn't make sense because position times time is like meters seconds. Meter second, bro. I don't know what that's I'm not going to talk about that. We're not going to talk about weird physics terms. Oh, talking about weird physics terms. So you get like, let's just say you had. This video is going to be longer, but who cares? Let's say you had a position versus time graph, right? Let's say it wasn't more than just like 1 degree of. Let's look at the velocity. That's also expanding non-linearly, right? So what happens is that then there's acceleration, which is also, how much the velocity is changing at this point. Like for example, let's say I take this point and I get that line through it. Imagine it's like perfectly on the line. That's going to be like the scalar value of the velocity at this point. Like the dot point, not the slope point, because you take this. That's going to be the dot point here. Anyway, for those degrees, like the instantaneous change in velocities, acceleration, and so on and so forth, but the order is pretty funny. It's in physics terms, it's position, velocity. I'm not going to draw them out because that's going to take a second. Acceleration, jerk, then snap, crackle, pop. Yep, that's not like, it's pretty official. Like you'll say that to any physicist and they're like, oh yeah, I know what you mean. But I don't think that's the legitimate way, but that's what my physics teacher said, so you can raise your qualms with him. So now we got over the derivative and the integral. Now let's just like say what they're useful for. Oh dang, do I broach related rates now? Oh, let me explain how the integral works first. So now, let's say you got that crazy position versus time graph. All right, time's here, and let's just say, let's explain what you're doing with the integral. With the integral, you have this function down where like, okay, I put in time, and it's going to give me a bad boy point, right? What it does, though, is it takes that bad boy point, and it makes it a skinny rectangle. I was about to say skinny A word, but I don't want to get, or I don't care about getting demonetized, but it's better for future use. So here now we have this like infinitesimally small thingy, right? That's why in limits, you'd say it approaches the width of these rectangles approaches 0. Actually, this isn't proper notation. Forgive me, like math people watching this. But let's just go on, right? So then you like stack these bad boys up. So you can go. Okay, so we're gonna go from 0 to, let's just say this bad boy was 7. It was 7 seconds. I know my scale is irregular here since I did like 6 hours in a Honda minivan. But let's just say we're in a Tesla, okay? No! I click back. Let's see if it's saved. Okay, it's saved. We're chilling. Hopefully this still works. Okay. You would go 0 to 7. 0. So that's. Let me regain my train of thought. We have this function, right? P of t. Because that's going to tell you the height of these guys. And then you like, oh my gosh, I'm actually teaching an integral. Okay, I guess I'll like include that. Oh my gosh, how to teach an integral. Clickbait, gone wrong, 3 a.m. Prank. Okay, anyway. So, and you tack on this little, because you're basically finding the area of these rectangles, right? And the height is just 0 to that point. So the height's just going to be that point that you found using your function, P of t. I'm not going to, let's say it's like 3t. That isn't too advanced. Actually, I'd be lying. Let's say it's 3t squared, since that would explain the exponential curve. Anyway, ignore my inane ramblings and let's continue. Oh my gosh, it's going to look like a 3rd grader drew this in the thumbnail. 0 to 7 seconds, P of t dx, right? Because you're basically going to add up these guys, and for an area, it's the height times the width, and the width is this tiny guy. Anyway, what this function does is you do like some magic behind the scenes stuff that I'm not going to explain yet, but you turn that function into a cooler function, and then you multiply by that, and then you do some stuff, okay? So now, that is the integral, where you take up these tiny lines, and you find the area. Because if I were to tell you, right, if you're in a moving car, and you wanted to find the position versus time, or let's do velocity versus time, because that would actually give you a legitimate metric. So we go back, go velocity versus time, right? And I were to tell you, okay, find the total distance. And since this is a regular rectangle, which you could go like, height times base times 1/2, you're kind of lost. But, your boy Rodman, what he did was like, okay, so we can take a point at like left side or right side, and we'll just like make big rectangles, which we will actually do by hand. Painful process. They'll still make you do it in calculus. But, it is what it is. That's how to cheat integrals. You just like, but it's a lot more inaccurate since there's a lot of, missing space if you do like that leftmost point. Because it could not account for like, that growth. So, okay, it's been 9 minutes of rambling. We've got through integrals and derivatives. Okay, let's go somewhere else. Now, since we're talking about integrals, let's say I had a function like this. Woo! That's so cool. Whoa, whoa, whoa. But let's say I spin it. And you're going to say, spin a line? Oh, what? But I'm going to tell you what that means. Let's say I spin this guy along this line. and let's say this is the y-axis, so I flip it around the x-axis, right? Which would mean, if we look at it like straight on, like imagine this was the line, it's going to do a circle. Boom, 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 boom. So, and what you do is this is called rotations of solids, right? Because you made a solid by rotating. I guess it's solid. Okay, never mind. That was let's go on. So you're rotating this solid, and using your super cool handy dandy integral. I keep on clicking my mouse shortcut. You guys probably hate me by now. I'll probably have to edit this. But let's go on. So, you take your integral, and let's see what you're doing when you rotate this. You're just having this thing, right? Actually, let me just... I might review the washer formula, the whatever formula it's called, because this was like a year and a half ago for me. Because right now I'm in multivariable calculus doing linear algebra this summer, then I'll do ordinary differential equations. So I'm pretty informed of this, but it's still fuzzy. So, but I know like the perspective, like where to go from there and what it really means. But so this is used, what you can do is now you're making little circles instead of little rectangles, you're making little circles. Because if you think about it, right, this bad boy, or let's look at its side view, right? This guy right here is going to be like this baby circle. This right here, bigger circle. But they're still like super thin. Like imagine potato chips, which aren't really potatoes at that point. It's just like these aren't really like any real thickness to them. But they're thin. And that means that you're taking the area, your good old oh my gosh. Okay. So I might need to take another take, but please forgive me. This is going to be, I'll make a second version. I just want to get one out there for my boy Stefan. So pi r squared, right? Because since you're taking the area of these like little potato chips. And then you add your handy dandy dx. Since we're using x in this case. We're going from 0. Let's make it 8 this time. Let's have some diversity in our numbers. Am I right, federal government? Okay, that was I don't even know what I was saying. But let's go on, shall we? Let's say this is from 0 to 8, and this r squared function, well, we need to find the radius. And let's just call this like f of x, right? The function that you put in a x, right? And a y comes out. Woo! So what we do there, okay, this is going to sound like I'm talking through a garbage can because my actual mic broke. You get this, right? You put in something, you take something out. But the thing is, if you're making a circle, you're getting 2 times the y because, it's like gadonk instead of just like this thing at the top. So you're going to put in a 2 f of x. I'm not sure if this corresponds with the actual formula because I haven't checked that in a while, and I actually shouldn't be going over formulas, but I'm just going to do it anyway because it's fun. Right? So we get the 0 to 8, right? And we get this bad boy, right? Since that's the radius now. That's going to calculate the radius. You plug in any of these numbers, like 0.1, it's going to give you this. And it's going to give you that area now, because you get the pi. Oh, wait, r. This part's r, right? Because the... Oh! Actually, we don't need it. You know why, guys? Because I was thinking about the diameter. But we all know d equals 2r. Learn something every day, folks. These things weren't made in some sort of 2001: A Space Odyssey post-death chamber. They're made by people thinking. Yeah. Wow. Anyway, so let's get that 2 out of there. Pi r squared dx. And we've got the shell method. Give yourselves a pat on the back. You just witnessed a raving lunatic. Look at our journey together, guys. Wow. I might revisit some of this stuff, but okay. Let's talk about related rates. This is often a Calc A student's worst nightmare. Or Calc 1 for all you international folks. If you watch this, this is probably not going to go anywhere, this video. Let's just assume someone would want to enjoy this commentary. Okay, so let's say you got this cool cone. Actually, I forgot the formula of a cone. But let's ignore that, right? So we got the volume. Some formula. I'll look at the formula of a cone later. Let's just say it's this squiggle. And then you got the, oh, okay, yeah, I remember this. So then, this is a very common thing, right? So normally with related raised problems, they're going to give you things that are related, right? It's in the name. So if you're, some of them are like, hey, you walk away from a lamppost, hey, and like, what happens to the shadow, hey, but like, I don't like that one. Let's do a cone, because we got a lot of triangles. Triangles are pretty cool, strongest shape in nature. Let's say you were given, they said, oh, the height, I mean, the height of the water, the depth or whatever you want to call it, this bed, like, see this here, it's going to go down. So like next it's going to be like, whoosh, and only that part's going to be filled, right? So the dh dt, that's the derivative with respect to time. And honestly, you could just write this as like, rate of, actually, why am I writing this out? The rate height drops in t. But in calculus, when you're talking about a rate of something happening, like the rate of the rate of position versus time, you're talking about the slope. The rate of velocity versus time is the acceleration. Oh, that should have been a better segment. That's what I should have said earlier. But I really don't want to redo this take because I think you guys are, having some fun. So the rate of the height falling, right? And let's just say that's like 3, nothing too interesting. Well, normally, how you solve this handy-dandy thing is you set out what they give you. Because the velocity is going to be, the volume. Jeez, volume is going to be some formula. Let's pretend it's like this. I forgot the thing of a cone, and I'm not going to derive that for you. This is actually of a sphere, I think, or the surface sphere. I forgot. I digress, guys. But anyway, you get a bunch of formulas, and then you find like the height is actually falling with a relation to the volume or something like this. And basically, what you do is normally instead of like actually thinking and solving these problems, what people do is they'll just take the derivative of one thing, and then with respect to time, where all the constants you'll learn later, they don't matter. Constants don't matter. Only the bad boy variables do. I'm sorry for saying bad boy. I apologize. I'll use a unisex term next time. Don't matter. So you get like 4 pi r. Why am I deriving stuff? Anyway, we're nearly done. Stick with me, guys and girls, and anyone who's watching. If the centaurs included. You're like other. You're gonna find that, oh, I don't know how the radius, because if you don't know something, like how the variable changes, you just say, oh, it's dr dt, right? Since like you don't know it, you're just going to say it's the rate this changes with respect to time. And then it turns out there's an interrelationship and everything turns out happy. The main goal of solving these bad boys, or bad problems, difficult problems, I have to break the habit, is just by going, I have to up the thickness here, I'll go red, is just listing out the different equations involved, and then seeing what derivatives you have. And then final thing, if you guys, okay, oh, guys, unisex term, please don't shoot me up. I'm California, it's a hard habit to break. Okay, one thing I didn't go over, limits. I'll just go over this right now in red pen, feel like a teacher. A limit is if this is approaching from this side and it's approaching from that side, this point, has a normal slope. But if you go like this, and let's say this point doesn't exist, and this point keeps going, and then the line keeps going, and like the actual point's here, that's a weird function. I'm not going to show you how that works, like mathematically, but let's say it happens. The slope at that point is still the same, because it's approaching like this line from that side, and it's approaching this line from that side, basically the same thing. So that's fine. But if it was going bonk, that's weird. What's the slope there? Is it going or is it going? We don't know. So that's why it doesn't work. So they're gonna say, is it continuous? Is it differentiable? And continuous is obviously just like there's literally nothing. It's not going in a straight line. But differentiable is when the point has to be there. Actually, this limit exists because it's coming from both sides. I forgot. This one, the limit exists. It is not differentiable, and it's not continuous. But non-differentiable means even if the point exists, right? Like, let's say this point exists. Like, every single point, the point's there, right? There's a point, and it's all in line. But if it's too wacky, you know, there are two different slopes from both sides. That's not going to work. Which one is it? Which slope is it? So that's basically why you have limits and stuff like that, to figure out what's differentiable, what's not. But normally you can think about it this way. Can a car do it? If a car can't do it, Newton probably realized that that's not going to happen in the ordinary world, and that calculus doesn't have to worry about it until you get like into weird things. Like, bro, why do I need to find the triple integral of a weird oobleck shape, man? Okay, so hopefully you stuck with me through these mad ramblings, and like Stefan, hopefully this wasn't like too embarrassing to show the class, but I think I explained almost everything. And I think I didn't really explain related rates, but I, kind of went over it by, oh my gosh, this is 20 minutes, by just explaining the technique used to make it as easy as anything else. Okay, I'm going to make another video probably.